So after covering the normal distribution and the probability distributions, and after covering the NHST, null hypothesis significant testing, after covering the t-test, chi-square test, and ANOVA. So today we are going to talk again. See, these topics are very, very slippery. That's why I shared with the experts. So, and today we are going to talk about one of the most confused things, correlation and causation. When we conduct the research, when actually the variables are causing each other, and when in which cases they are just related. And though it is very tempting to say correlation is causation, we should not, and why we should not. So that's we're going to learn. And after that we are going to learn the regression in very, very rough, and especially linear regression, right? And by that we'll be ending this our winter school. So without further delay, I welcome both our esteemed instructor for today, Dr. Cecilia and Dr. Kavita. So session is over to you.
Hello, good morning. I hope you're doing well after yesterday. And I also wanted to say that if there's still some open questions from yesterday, feel free to ask as well today or now while I prepare everything. Just let us know. And yes, I will start sharing my screen. Give me a second because Google, it's not my favorite thing. Google Slides. All right, I think I can share this. Yes, super. I do a check while, yes. Well, you see my bar up here, but that's okay. That's all right. Okay, we are ready. So, welcome. And yes, today we are gonna, yes, same housekeeping rules as yesterday. Ask anything, anytime. Don't, like, I was talking yesterday evening with Kavita, and we were really impressed, and we really liked that you were so participating with us yesterday. So please don't stop. Write it in the chat, raise your hand, and yeah, anything. And if you are stuck on a code error like yesterday, you can paste the error in the chat, or you can let us know. We can have a look. Yes, and you can also try to answer each other's questions in the chat. And today we will divide the morning into correlation and causation, and we will do a bit of lecture, and then we go into the R script, and same in the afternoon, regression and regression in R. And now, like Ajay said, regression can be different things. Today we will focus on the linear regression because of time, but I am confident that while you will have then the basic then to go over the other yourself. Anyway, so this won't sound very new to you because we've been talking about this all over yesterday, and also probably before, in the days before. But when we collect data and when we use today, for example, we will use prepared data sets. We always have variables, and variables is simply anything that we can measure that it changes, and it can take up to different values. And we saw, for example, some example yesterday's. Variables can be heads or tail, and it can be salaries, it can be heights. Today we will see countries can be variables, anything that can change and can take on different values. Today we really need to understand this concept that is really, really important. So in science and in statistics, we never are interested in only one variable. We always want to know very often want to know if a variable A has anything to do with variable B. And if one follows the other. So if one increases, the other increases, or they ignore each other, they are just completely independent. Yes, so, and this is what we mean by correlation, because correlation, as the word says, is a measure of a correlation between two variables. When, for example, if you focus on the first plot, when x increases, epsilon increases too. So in this case, I can see that in the first graph, there is positive correlation between x on the x-axis and y on the y-axis. On the opposite side, if I increase the value of x, the value of epsilon decreases in the second example. This means they have a negative correlation. So when one increases, the other decrease, and vice versa. And then there's also the option that there's no correlation. Like the two values are completely independent. They don't follow each other and they do their own thing. There is in statistics a method to measure the correlation. It's called the Pearson coefficient. It's a number that we call R, as you can see in the plot. And we know that if this R is 1 or is very close to 1, the variables are perfectly correlated. For example, in this case, this would be an R very close to 1. And this will be an R very close to -1, the negative correlation. So if it's the R is positive, is from 0.1 to 1, it's always a positive correlation. And if it's negative, it's a negative correlation between these two variables. If it's equal 0, it's the third case we saw before. There's nothing that puts together these two variables. So they don't influence each other. The thing you need to remember from today is that you will probably never find an R that it's completely equal to 1 or -1, because in real world data, this is very unlikely situation. But in real data is always noisy, and there's always something confusing about them, and that's also something we will practice today. Because sometimes you think you are studying two variables, but in reality you're studying something else. So you always have to keep an eye on what are influencing my variables. But then, like Ajay said, we have correlation. Is there other questions or anything? Okay, good. So correlation is one thing. If we see this plot, we can say, yes, there is positive correlation between X and Y. But how can I know which one is influencing which? So would it be that X is influencing Y? So if I increase the value of X, will epsilon also increase? Or is the opposite? Is epsilon influencing X? I know that with this very abstract examples, it sounds like it's the same thing. Is one influence the other, they both increase. But it's not. It's very important. And we will do some real life example later to help you understand this difference. And there could also be the case that two variables are perfectly correlated, but there's no relationship between them. So they are not influencing each other. And this is what we will learn today. So this is what distinguish correlation and causation. If two variables are only correlated with each other, meaning they are moving in the same direction, then doesn't mean that there is a cause effect behind these two variables. So when we talk about causation, we mean that there is a cause-effect relationship between the variables that I'm interested in investigating. So when there is causation, there is also an underlying of correlation. So two variables are correlated first, and then there is might be a causal link between them. So two variables that are linked by causation are also correlated with each other. So another way to put it is that if X causes Y, if and only if I change X and it also changes Y, all right, while keeping everything else in a vacuum. This is the mantra that you have to keep, like, bring home with you, bring everything you go. Correlation does not mean causation. This is like the first and foremost law in statistics. I think it's easy to say that. And this is a comic I found online. I find it very funny because I used to think correlation implied causation. Now I took a statistic class and I don't. And the friend said, "Sounds like the class held." Well, maybe. Maybe the two variables of me learning statistics and knowing that correlation implied causation are not correlated with each other. Maybe are not cause effect. Maybe are just correlated. So we need to do a test, a model to see if this is true or not. Another way to see it, and that's what we will focus on today, like in the first part of the morning, is the directionality. So in the previous example, I was talking X and Y, now I talk in A and B. So when we see a link, when we see that A and B are correlated, for example, we might not know the flow of the association. So, like I said before, is it A that is influencing B increasing, or is B influencing A? So if I increase, which one should I increase to see the other one increasing? Sometimes it's only one direction of the two. And that's what causes the causation effect. For example, people carry an umbrella and there is chance of rain. So, for example, which variable here influence the other? Does the umbrella, like me bringing an umbrella causes the rain? Or is like the chance of rain that causes me to bring an umbrella with me when I go out? This is a very silly example that it's clear to see, right? There are some things that are like, yeah, it's obvious. Of course, it's like me bringing an umbrella won't cause to rain, or like, yeah, logically, of course, so anything could happen, but logically, the chance of rain causes me to bring out an umbrella. But there are some others that might be a bit more tricky. So you have to really think. For example, and this is what you will see a lot, like we see it every day in biology, and because, of course, if you have no knowledge, you don't know, you see two events and you don't know which one is influencing what, but it's the same in social science. So in this case, children watching more TV is correlated with lower grades. So, does the TV make you study less? So, the more time you spend on the TV, it makes you study less and then causes the lower grades. But it could also be the opposite. It could also be that students who struggled with grades procrastinate more and watch more TV. So in this case, we don't know. If we see a relationship like this, we might need to test, like, what is causing what. Before we draw any arrow or we assume any causation, we need to do to check. But then, of course, we need to add complexity, because in real life situation, it's very rare that two variables influence each other in a vacuum, like we said before, that nothing else is happening. Usually there are other variables interfering with either X or Y. And this interference we call confounds. And in this case, that is our confounding variable. For example, I put here a silly correlation of like ice cream consumption and sunburns. If you see the plot, you might think either the more ice cream I eat, the more sunburns I get, which doesn't sound right. Or the more sunburns I get, the more ice cream I eat. Which could be, yeah, maybe, but what is the relationship there? But so what could be like, what could be a confounding variable here? What could be influencing climate? Yes. What could be influencing me eating the ice cream and getting a sunburn at the same time? Like, yes, the sun, or being a summer day. Yes, temperature, exactly. Oops. Yeah, a summer day influences both in a way that they don't influence each other. So this is important to remember that sometimes you're studying two variables. We will see a lot of examples today, but they have no real link. You have to think if there's something that could influence both in a way that they will move in the same direction and be correlated with each other, but they will not causing each other. That's why we always say correlation does not imply causation. What I used here all along are called DAGs. DAGs are directed acyclic graphs. What does it mean? Is like it's just a way to represent these relationships. And in general, I find them very useful to keep my head clear sometimes. I have a lot of variables and I'm not sure what is going where. And so we use these DAGs to make things less messy. And it's just a fancy word for boxes and arrows. But it helps visualize the risks we saw, like of having unclear relationship between variables. So yes, is a great way to do this before we touch R and before we are going to write any code, because I think it's better to have it mapped out before you start writing in R that does a lot of things behind the scenes, and you really have to be careful and you have to think not 2, 3, 5 times of your variables, what could be the confounds, what could be the directions of the arrows, because the acyclic part of it means that the arrows don't go in circles. So there should be no loops. So in here, I cannot put an arrow that goes to Z, from Z to Y, and then from Y back to Z. No, there should be only one direction and no cycling loops. All right, questions about this before we move? Good. Now we will practice making DAGs. So I will give you a list of some examples. They are like very silly examples. And for each example, I want you to identify the variable X and variable Y, and determine the relationship, so the direction, the arrows. And if there is an hidden confound, you can name one. And these are just examples. So it's completely fine if every and each one of us come up with different confounds. There's not probably gonna be one right answer. But if the relationship between X and Y is completely unclear, there might be a confound that has effects only on X and only on Y. it could also be that they follow a line. So the confound first has an effect on X, and then that, as a consequence, has an effect on Y, or something in that direction. All right. I will leave this here. And I was thinking, what do we do? 10, 15 minutes for this exercise? And then we can
Yep.
go over it together. I have the answers in the next slides. Or wait, in 2 slides.
Yes.
And of course, if there's any question, something you don't understand, please write in the chat.
And if you happen to be discussing it amongst yourselves, you could also share it with us on the chat so we can think together if you like.
Yes, exactly. You can also do it in groups. Absolutely. I'm sorry, I just realized that I didn't say what direct and reverse is. I think I glimpsed on that. What I mean by that is that direct is like variable x to variable y, so a direct positive relationship, and reverse is on the other side, so y to x. Sorry if that wasn't clear before. It's too early here. How are you guys doing? Should we do 5 more minutes or are you done? Oh, yeah, for the first one, yes. So I would like to see, I found a message. Mm-hmm. Yeah, nice, very nice. So I would like to see if you go in the chat, I just put a message with done, and I would like if you can put the thumbs up when you're done. You can just click on the one I left there with all 10, but no rush. Take your time.
And if you have any questions, or if you don't understand any of the things, you can just leave it in the chat. Like, why
Yeah.
should this, even what should this mean, or something like
Mm,
that also.
yeah. Mm. Very nice. I'm just going through the chat. Everybody had super answers. Very nice. It's also a great exercise because you will see there might be, even when the effect is direct, there's always confounds variables. In the world we live in a very, there's always variables around us. So we can always think of something. Yes, exactly. Super. I didn't see any for number 8. Does anyone, number 8, fire? Yeah. And number 9, severity of disease. All right. Number of crime rates. Very nice. So, thumbs up on the Zoom if you're done with the exercise. One thumb. A lot of thumbs. Very nice. Yeah, I keep seeing there's answers coming up still, but your guys are doing great. Oh, wait. No. I want to make the. Oh, wait a second. I need to put this. Hmm. Anyway, we'll make things works today. No. Anyway, all right. So, as you can see now on the screen, I hope, yes, there are the solutions. So, we can go over them one by one. And if your Z was something different, no worries. It's correct. We went through the chat and the answers are correct. But as I said, most of the time, sometimes there are confounding variables that could be different levels. So that's all right. So areas with high ice cream sales see more shark attacks. And so, of course, it's the Z, so the confounding variable has effect on both. And I wrote summer, but of course, some of you put also the location of the ice cream stall. Yes, because if it's near the seaside where shark attacks are more likely. Could have been like summer day or temperature or, the location. Yes, absolutely. In Europe, regions with more storks have more human births. And of course, storks and birth rate have nothing to do with each other, but the areas, so in rural areas, there's more wildlife and more storks nesting on the roofs of buildings. And I also want to share this because I don't think it's common knowledge. In the past, when, like, at least in my region, I come from Italy, it was very common to turn on the fire, even in summer when there was a newborn in the house. And that is because newborns needs like a lot of warmth and a lot of boiled water, tension, and everything. And storks were used to target those chimneys because they were warm to make their nest there. So that's also an association on the fact that storks nest on a warm chimney that has a newborn in it, and that's where the association also might have started. People who carry pocket lighters have higher rates of lung cancer. Of course, no association between having a lighter and having cancer, but there is a strong association between smoking and having a lighter and smoking and having lung cancer. So yes, this was correct from all of you. Neighborhoods with the most police officer also have the highest crime. I saw a lot of you wrote reverse, which is correct. We could have also accepted, for example, a Z in which poverty would have been a confounding variable because more poor neighbors have both higher crime rates and also might have, because of that, also more police officers or presence of police. So this was the number 5 was tricky, and I'm so happy most of you got it right because when I first saw it, I didn't. So sleeping with shoes and having a headache, of course, if you alcohol consumption or a hangover, so the more time you sleep with your shoes on is coming home late at night by when you had too many beers. And so there is absolutely no relationship between sleeping with shoes and headaches, but there is by having a hangover and having a headache and sleeping with your shoes on. Then, students who spend the most money on private tutors often have the lower average grades. And I saw, I think, let me check in the chat, I saw, yeah, that most of you said, yes, of course, getting lower grades causes parents to hire a tutor. The tutor does not cause the grades, the lower grades. So, correct? The reverse?
That also makes sense. Yeah.
Yeah.
No, that also makes sense.
Yeah.
And in this
I-
case, maybe a strong confounding variable that more screen time, because today's, maybe because you have a tutor, but still your grades are low because you have more screen time instead of screen time, maybe.
Maybe, yes, of course. And that's also why I wanted to, yes, I like that somebody come up with new ideas because that's exactly how I wanted to do this exercise because this is what I thought was, yeah, reverse. But yes, of course, there could be confounds variable, and this is a great one. Also, like if I think it could also relate it to having a tutor, right? Because it could be that if your tutor is online and you pay zero attention, your grades don't go higher, for example. So yeah, nice, thank you. People who are taller generally have much larger vocabulary. I saw all of you said age, which is correct. The taller you are, the older you are, and so you have more vocabulary and better vocabulary. Here I saw some uncertainties here. Number 8, the more fire trucks that show up to a house, the worse the property damage. This was, of course, it was very simple if you think about it. So the Z, the confound was the fire. Like I saw some of you put it, and some said the reverse. Well, the fact that the fire truck are there are only because of the fire. So the size of the fire might make more damage, and so call for more fire trucks. So the severity of the fire or something like that. Yes. Patients in the most specialized hospitals have often higher mortality rates than in small local clinics. Yes, to all of you that said the severity of illness, because when you go to a more specialized hospital, often is because you have a very severe illness that is not easy to treat and that brings into a higher mortality that has nothing to do with the hospital, but has to do with the kind of illness and the severity of your illness. And then, because there was just to make things more complicated, the only direct one that's the most simple. Coffee drinkers appear to have higher heart rate. This is a direct causation that we know since many years that coffee causes higher heart rate. I saw some of you also put like exercise, making exercise. Yes, could have been a confound variable because if I am an athlete, my heart rate, my base heart rate is higher than somebody who is not. So yes, that could be a great confound. And yes, it's something to keep in mind always. Nice. Super. Was there any problems doing this exercise? Was there any questions that came up or something that doesn't really make sense? I think it was, I mean, from what I saw in the chat, all of you did super well. Confident.
Confidence instead of age. It's also
Ah,
nice.
this I like. So taller people, because they also being tall, sorry, being tall brings you maybe also more confidence. And yeah, could be like on a triangle, like tallness brings you confidence also, and tallness bring you to speak more often. Yeah, something like that in that direction. Yeah.
Yeah.
And I was thinking also, yeah, one of the classic, I didn't put it because I thought yesterday we talked already so much about weight and heights, but that's a classic one. Re-explain number 6, of course. So students who spend most money on private tutors often have lower average grades. So in theory, or if you think of parents, their kid has lower grade, and that's when they hire a tutor. So the cause is the lower grades that brings to hire a tutor. So if you think of it as a cause-effect relationship, so the cause is the lower grade and the effect of that is to hire a tutor.
So here the Y leads to X, and that's why it is also a reverse task.
Exactly. Um, yeah, there was weight and height and how they influence each other, but there are a lot of confounds within because as you can imagine, if you imagine it to put it in a plot, if you have a piece of paper and you put it in a plot, and it's like the taller you are, the more you weight usually. But there are confounds in here which are, for example, gender. In average, women weighs less than men, so that's a big confound in this relationship. All right. Any more question? I see Kunal has an emoji, but I don't understand it. I'm too old. Super. I see like a forward. All right. We have 15 minutes. We can move forward to this part and then we keep our session for later. All right. With this we said yesterday already, and we will repeat it throughout the day today. It's very important to visualize your data. Usually when I use my own data, the first thing after reorganizing my data set and tidying, the first thing I do is to plot it. Of course, it can also bring confounds because of what we said yesterday, that humans see patterns everywhere where they don't exist. But this is a good first step always. So you have to you have to plot and you have to bring objectiveness and how is it called when you are skepticism. So So for direct relationship A to B, yes. For reverse relationship B to A, yes. For confounding is C to A and C to B, but not A to B. So it would be C to B and C to A in this case.
I think the
Of
best
course,
example here is the one that you showed, the circles. I think that was very clear.
in this case, like this, if you
Mm.
remember this, like summer day, ice cream, and sunburns. And of course, this is the easiest of the scenarios. That could be like when you have 3 or 4 confound variables, they all interact in different ways. But let's keep it simple for now. But yes, the point of why these two are not related is because, and that's why the DAGs are very important, and why I like to do the DAGs is because you can't put another arrow in here because otherwise you will make a loop, right? So it's a way to put it so makes you think like, okay, it has to be unidirectional. Yeah,
Yeah.
exactly. Well, yeah, also that's another, yeah. All right. Yes, visualize your data always. It's very important. And yes, as I said, you have to look at plots with skepticism, objective. You have to be objective and you have to like really think about what you want to see and what you want to investigate. Because if you rely only on numbers like the Pearson coefficient, which I remind you tells you the strength and the direction of the correlation. So if R is close to 1, it's a strong positive correlation, and if it's close to -1, it's a strong negative correlation. But sometimes this number cannot really tell you anything important, and I will show you some example. No, this is the basic example. So R is very close to 0.8 in this example because it's like very strong positive relationship. So sunny days influence the ice cream consumption. But an R of 0.8 can also be not related to a strong linear relationship, all right? Because as you can see in this plot, you have the same identical R, so it's always 0.816, but once you plot it, you see that there is something off. So the first one looks like a correlation. Yes, there is on one increase, the other one increase, it's a bit noisy, but it's strong on the line. In the second one, it looks more like a curve, right? Actually, it looks that the more the x increases, at some point, epsilon decreases. So it's not so strong. In here, it's in the second here on the bottom, it's exactly the example we were giving yesterday. Sometimes you have outliers that make you think that you have a relationship, but actually there was none all along, right? It's just this one point that it's pulling everything away. And the same thing with the third one here. Like the line, because of this outlier up here, it's much more tilted towards the top. Without this point, the line would be more flat, and so the R would also be lower. This is a great example. It's called Anscombe quartet. These 4 data points have all the same numbers: mean of x, mean of y, Pearson correlation, and regression line are identical in all four, but the data is very different. So we can use DAG for visualization, coefficient score for analysis. DAG for visualization, I think you should use DAG for yourself to make you understand how the variables are connected and where the arrows are going. You don't have to. It's not a prerequisite. I find it very useful, but it could be also like how we did it here. You didn't need to make a tag, right? If something was confusing, maybe you would have put like the box and say, okay, these three are here. How are they connected? In which direction? But you don't have to. It's an exercise for yourself.
It's
And
often useful when you make your statement like we saw yesterday with the hypothesis. When you make the statement and then within that statement you can think about your variables, and it's often a good practice to actually write it down or list it out, what is an X, what is a Y. If there is a confounding thing, then that kind of leads you to, because if you don't know what the confounding thing is, then that is a research area. So it's good to know what are the other factors.
that could influence, yes. Does that answer your question, Mohit? Yes. Thanks for asking. Yes, keep them coming. So we were saying that these have all the same values, but the data is very, very different. So it's important not just to rely on the numbers and on the analysis, just on the p-value, just on the TD statistics and things, but also look at your data and let it show what it wants to show. So as I said, this is like a very good example is called unscoped quartet. It's for this different data set. There's 11 points each. So, but it's a principle introduced by this statistician that showed exactly what the importance of visualization. Okay, last 5 minutes. We can just quickly talk about this. This is the other thing why we always plot and why you always want to see your data. Because a correlation can be positive for the whole population, but within this population, you can have subgroups and where this positive relationship doesn't exist. So if you see in this example, it's the same points in both graphs. But if you aggregate everything together, you can see, yes, there is a linear relationship. If I increase Y, I increase X, super. But once you see that maybe these are different groups, these are different locations, different populations, different I don't know, score test, something. Then you see that actually within each population there is a negative relationship between X and Y. Can you go through the last slide once again? Yes, you mean this one, the Anscombe quartet, or the Simpson paradox? I will maybe restart from here. On this one, you mean? On the R Pearson correlation and everything before the Simpson. Yes, okay. So this one, I think it was, maybe let me go back 1 second, when we talked about Pearson correlation. Pearson coefficient, yes. So this as a reminder, we saw it very early this morning. Pearson coefficient is a number, we call it R, and it just shows the direction and the strength of the relationship between two variables. What does that mean? It means that each variable, two variables that are correlated with each other, have a value of Pearson that is either close to 1 if the relationship is positive. So, for example, here is towards 1, 0.7, and it's negative if the relationship is negative. All right, so you can see it also from the side of the linear relationship. So a number closer to 1, it means that the relationship is stronger. So in this case, we have a lot of points close to the line. And in this case, it's lower at 0.3. The points are more scattered, far away from each other, but still there is a direction in that. When it's 0, so it goes from -1 to +1. And when it's 0, there's absolutely no correlation between two values. So once we know this, we might be at risk of saying something like this, right? Once we know, well, there is Pearson, I just look at Pearson. And I just look at Pearson and I don't need anything else. And in most cases, it's okay, because in this case, ice cream consumption and sunny days, it might have a Pearson of 0.8, and it would be correct. Like there is a positive relationship between these two variables, and the Pearson shows that. But some other times, if I only rely on the Pearson number, I don't see the full picture. And that's why it's very important to visualize your data. In this example, there are 4 data sets with 11 points each that have the exact same Pearson coefficient, the exact same mean of x and mean of y. So all the values that we saw yesterday, that we were looking at yesterday, and that we learned today, the Pearson correlation coefficient, is everything is the same. So it should always be a positive linear, positive correlation, but it's not. Because if you look at the plots, the only one that shows positive relationship is the first one, where the points are, if you look at x, you increase the number of x. So at any increase of x, y increases as well. This is the only case of positive correlation. The other ones are a bit with noise. So, for example, the one below, you could say, yes, there is a positive relationship. Yes, you would be right. But the point is that this outlier here, it's pulling the curve, the line, higher than it should be. It should be probably aiming in this direction. Can I maybe? Yes, it should probably aim in this direction. But the fact that there is this point here, it's pulling it up. So it's not correct, right? We have to investigate what is this point. Should we keep it? Is it important? Is a error measurement? Can we ignore the outlier? Yes, it's a good question. And there's no answer for that because it depends. It depends on the case. So let's make an example. I am investigating the number of sunny days and the ice cream consumption. I see that the more I increase the sunny days, the more the ice cream increases. But then there is this point, and this point could be that the temperature of this day was very high. So it was a confounding variable. And in that day, there were an immense number of ice cream bought. So I can't remove this outlier because it's relevant to my question. But it could be that this outlier, it's because that day I wrote down a wrong number. I wanted to write 8 and I just wrote wrong in my notebook, and this we call it's a measurement error. So in that case, only in that case, I can remove this outlier because I said, yeah, I just wrote it wrong. So I have to remove it. Actually, I have to remove it because it's not relevant to my research question and it was a mistake. So in that case, you can remove the outlier and then you can get the nice linear relationship. And then the R in this case will not be like this anymore, it would be a different number, but it would be more correct. Is there any other?
I
Yes.
could add to that as well. Like even with the outlier, like it could also be that like that particular day, like yeah, temperature is one thing, but it could also be some other confounding variable. Like say the ice cream guy was having a sales day, or there was
Yeah.
something like like say there were tourists in the spot that you didn't expect at all that particular day. It was a holiday, like yesterday, like a Republic Day. It was a holiday, and there were lots more people than on a regular day. So, yeah, in that case, it's very difficult to say, like, yeah, do you keep the outlier or not? But but that is, that gives a scope for explanation. Then you say, yeah, it was a holiday, and that's why we saw that spike, and that's why it remains an outlier. Yeah.
Yeah, no, exactly. This is a perfect example. Like you don't have to always remove the outlier or ignore it. You can explain it and say, okay, when you write your paper and you say, yes, the R is 0.8, I know that it should be lower, but I have an explanation for this outlier. It's because that day it was a holiday, blah, blah, blah. And this would be completely acceptable. Yes. Is there any other correlation measure which can mitigate this issue? I mean, yes and no. I think we will see today, like we will learn how to make models, and I think all together will give you a better picture. So you have to look at all of this thing all together. So there's not one measure which can help you explain something. Can you explain regression line? No, later. We do the regression part later. I know it's a bit confusing because it's all together, correlation, regression line, and everything. Ignore this for now. It was just to say that they have all the same values, but this we see in the afternoon. So ignore it for now, and yes. Any other question about this before we go for a break? I think we have 30 minutes break, right? And then we can go to Simpsons and R.
Does it work with
Yeah.
everybody? A 30-minute break now, or
I was looking for.
Ajay? Yeah.
We have 30 minutes more, but if you want to take a break, it's
No,
okay.
20 minutes more.
Yes.
No, that's perfect
Sorry. Yeah.
Yes.
because I can finish this part and then we move to R.
We can maybe do a 5-minute break or something
Yes.
and then
Yes.
continue,
Yes.
because then we
Yes.
yeah.
Let's do it. Yeah, perfect. See you in 5. All right. Let's do it. Last 15 minutes, we can just have a look at the last concept I have, and then we go for the longer break. Let me open this. Yes. Perfect. All right. Any questions about this? Are we clear? So we will see some examples of this later in the R session. But yeah, just want to say that sometimes, of course, sometimes the visualization can confound you, but sometimes it's good to visualize because, yeah, you can see that something is off. For example, in this case, where this curve is not positive relationship anymore, And this curve it's also not a curve. This is also what an outlier does to a data set, right? So this is just something important to keep in mind. And I need to remove these marks now. All right. If there's more question, please ask. Otherwise, I move to this. This is also a very important concept. I see this done all the time, and we will have, while working on R, can all of us refer to work on the same data set like yesterday? Yes, we will work on the same data set today. We will load a data set from R. It's called Gapminder, and we will all have the same results then. Yes. Super. So this is a great example. This is something we will do also later, but I have a plot from R about this. So let's take as an example the whole word. When you look at some variables and you look at the whole word, you might see something like this, a positive trend of I don't know, health per life expectancy, health and wealth. So how much money a country has is how much is life expectancy is. But once you divide it by countries, for example, you see that it's not true anymore because each country has its own negative relationship. And if you ignore this hidden confound, then you make an assumption that is not true. So I have an example about this, but just to remember, this is called Simpson's paradox. And it's also sometimes not for whole word. It could be, for example, you are testing a class and you have all the individual in that class, but then the confounding variable could be gender or something like that. And so you might see like, the class score is higher the more, I don't know, height, I don't know, of the student, which makes no sense. And then you have the subgroups of gender, and then you say, okay, there is a gender doing better than the other, or no, and both genders are not doing great. Actually, the relationship is negative. All right. So this is something to keep in mind. It's called Simpson's paradox or the aggregation trap. Yes. So the bottom line is don't trust the numbers more than your eyes. And this is also a great example I found on the internet in which, as you can see, the numbers of mean and standard deviation and Pearson are the same to the second digit. What changes are the lower digits, but somehow the visualization for these numbers can be anything. And as you can see from the animation, like all of this positions of these points is consistent with these numbers. So never trust only the numbers. The numbers don't tell you the whole story. You need both. You need the numbers and you need a good visualization method. Yes. So real world data. This is the data set we will work on today. It's called Gapminder. And inside this data set, there are real data collected from people. Then they put it in a R package. And I show you this because so far we saw these beautiful plots that all the points align and everything is magnificent. That will never happen in real life. That is because real data is noisy, it's messy, it's full of hidden confounds, and you always have to keep an eye on what you are testing. So in this case, you can see this is the example we were making before. We have life expectancy and we have the GDP per capita, so how wealthy the country is. Each point is a country in the whole wide world, all right? And so, as you can see, if you only see this plot, you could say, yes, well, the more a country is healthy, the better the life expectancy is, right? But what about, what are these countries, right? So if we color code each point for to the continent they belong in, we actually see a very different story. Because Africa has a very, very strong relationship between these two. It's almost like, and it's almost like a vertical line. What does that mean? It means that by a very small difference in GDP per capita, there's a huge increase in life expectancy, right? And this is because, like, at that level, when a country is so poor, anything can make a difference. Having like paved road, having, I don't know, a tiny local hospital, this would make the difference in 20, 30 years of life expectancy with a very low change in GDP per capita, for example. For European countries that you can see in blue, the line is so much less strong. Why? Because in Europe we reached a point of which of human health in general, we cannot go better than that, probably. And even the wealthiest country cannot really make a difference with the poorest country in Europe in terms of life expectancy. So at that point, money doesn't matter anymore on investment on the population, because there's not going to be much difference between the poorest country in Europe and the wealthiest country in Europe. In Asia, the green points it's something in between, for example, something in between Africa and in between Europe. Why? Because in Asia, like historically, there are countries that are all over the wealthy map, let's say. There are countries that are very, very wealthy and countries that are less wealthy. And so there is this difference is going on a gradient there. The countries are moving towards a better wealth, and so the life expectancies is getting higher. All right. So in this case, we have the difference between this of everything in the same pot and this colored by continent. So we can, like, just by making a plot without having any numbers, we can make a lot of assumptions. Like I talked the past 5 minutes about this plot of what I see in this plot, just based on the fact that I colored the dots for the different countries. All right. Are there questions about this? Is this somewhat clear? We will make these plots also later, so we can also investigate this a bit further. But yeah, I think this is okay. Or
I think the Simpsons paradox also applies here because, like, yeah, these are all the countries in each continent. But if you actually list out, the states in a country, for example, and just
yeah,
list out per country as you showed, like the different groups in a country, I think then maybe your data looks different, like
yeah,
that could
that,
also add to the explanation.
yeah.
Yeah.
Yes, Ajay, tell me that.
And one point from the perspective of methodology, that's why when we collect the data, we should make sure we should have some categorical variables, so that when you collect those numerical variables, you can plot some categories and you can divide into some subgroups, because these are the categorical variables which have been plotted on the numerical data. So so that
Mm.
yeah, thank you.
No, thank you. Yes, absolutely.
That's There's another question. Will the Z be very different in every continent? Examples. Yeah, I think that's what I was mentioning, right? Like the different countries themselves can have like different values as such, like the life expectancy, this correlation that you see, like each data point can be different based on, say, states in a country or regions in a country, and so on.
By that you mean that score, or you mean what? Because yeah, I'm sorry, maybe it's also my fault. We use that in so many different contexts today. Just example, yes, but for Z you mean Z scores or Z as hidden confounds?
I think hidden confounds as it is in this, what makes Asia sit in the middle?
So each point is a country. All right. So Asia has India, for example, but also China, but also
Japan.
Japan and Singapore, and I don't know, many, many different countries. Each one of these points is one of these countries. And they all come within the category Asia because of where they sit in the map. So between or I don't know, Cambodia, Vietnam, Thailand, all of these countries have different wealth. Like historically, a country like Japan is like very wealthy, or Singapore, I guess it's one of the wealthiest. So they will sit very high up here. Wait, up here. I don't know, but I expect that these countries would sit very high in the GDP per capita, right? Because I assume that they are very wealthy. Countries that are less wealthy, now I don't want to make any assumption though. What could be an example of a country in Asia that, I don't know, Vietnam, that are less wealthy than Japan, for example. India could be that it's a bit less wealthy than Japan is, or
Countries like Afghanistan, Pakistan,
Afghanistan. Yes, thank
these are
you.
very poor
Exactly.
countries. Yes. And
Yes,
the
Yeah.
rich countries could be also like Saudi Arabia, Qatar, because they are very
Yeah.
rich.
Yeah.
they will
Yeah. True.
here, right? Qatar, Saudi Arabia, like those are, in my perception, a bit wealthier. But something like Afghanistan would sit maybe not here. I don't know which country is this, and I don't want to offend anybody, but let's say it's a country that is very poor, has very low wealth. This would be the exact scenario in which it's like we said for Africa, that a very small gap in wealth can make a huge difference in how the life expectancy is. And by life expectancy, I also mean like health, general health, right? Because if you invest in your country and you build a hospital, that maybe it's not such a big investment for a small hospital, but it can have a huge, like this small investment can have a huge effect in life expectancy. Or something very silly, vaccines. One of the first causes maybe is like vaccinations, like you get, or antibiotics, something like that. Very poor countries in Africa might not have access to those, but it takes a very small investment to get people into a very higher life expectancy. And that's why the confounds is so important, because in Africa, if we would only plot, maybe I changed the color, I would only plot the Africa line would be something like this, right?
Yeah.
If we would only plot the Europe one, it would be something like this. But if we would plot Asia, it would be in between, because it starts from here, it goes up here, and then it floods like that, all right? And why is this? This is because at some point you reach a point when you're 70, between 70 and 80, that there is not much you can do. Even big investments in, or like a big wealth in the country doesn't make much difference in your life expectancy. And this is where, for example, Europe sits. There is not much difference in life expectancy between the poorest of the European country with the wealthiest of the European country. And I think that's also where like some Asian countries sit.
Yeah. I mean, in fact, you also see like some African countries between the 70 and 80 mark, you see some red dots also, you know.
Yeah,
So
exactly. Up here,
so
they
it's
are
not
moving.
like entirely, yeah. So, but again, like if you, but you also got to see the GDP per capita. I mean, it's not so, yeah, so well
Yeah,
off, as compared to
of
say
me,
some
for
European
example.
countries.
Yes.
But
Yeah,
yeah, so I think, yeah, like it's also some things into consideration rather.
exactly. Is this more clear? Yeah, it's the same for the Americas, right? I feel like this is a great example because there are some countries that are here and moving towards this direction, and some countries that are in the in-between phase, like Asia, it's in between, and Europe, that is like the last step of the, and Oceania, those are the last step of the where the other countries are moving towards, right? As wealth gets better everywhere, they will move towards this line. And maybe in 20, 30 years, if nothing major happens, which, yeah, we will all flatten out here. All the countries will move there and then just be flat there. All right. Use another example is this. This is in the log scale. So what does that mean? Usually when you have data distributed like this, you can convert them in the log scale and put them like in a very easy linear relationship. This is the same data, all right? It's the same data as this, it's just converted into the log scale. We will do this today as well. Usually there's not many not that I can think of, not many bad things could happen if you turn your data into a log scale. If you have like very big data set with very big differences, usually if you turn it into a log scale, you can have a more clear linear relationship. But yeah, this is a great example. Like the global correlation, Pearson is 0.6, but that's a bit too high for Africa, which would be a bit lower. And it's a bit too low for Europe and the Americas, which would be a bit higher, and Asia as well, right? And yeah, I hope this didn't confuse you more, actually, but it's the same data set. It's just a different, as you can see here, the GPT is turned into a log scale. All right, so I think we are up for our 30 minutes break, and then we will move to R. We will use this data set called Gapminder. If you don't have it, no worries, we can do it together. And then we will do these exercises to understand the relationship between variables and finding confounds, and also plot it in a way that we can visualize it better.
Yes, sounds good. Let's meet after 30 minutes.
Super. See you later.